So far, when integrating, if we've come up against a difficult integral, we've used the substitution method to make it a little bit simpler. We're going to be looking at a method called integration by parts in this video. So substitution is based off the chain rule of differentiation, and integration by parts is based off the product rule, which, as we know, states if we have some function uv where u is a function of x and v is a function of x, and we want to differentiate it with respect to x, then what we get is the first function, u, multiplied by the derivative of the second function, v dash, added with the reverse of that, so the second function, v, multiplied by the derivative of the first function, u dash. So this is the product rule for differentiation. But what we can do is manipulate this a little bit and do some rearranging. So let's first start by integrating both sides of this equation with respect to x. We can see on the left-hand side that the integral and the derivative cancel out and leave us just with uv. On the right-hand side, we have the integral of both of these terms. So we have the integral of uv dash with respect to x, and we also have the integral of vu dash with respect to x. If we then decide to make the integral of uv dash the subject, then that means we've subtracted this integral from both sides. So we have uv minus this integral, vu dash. And this is the rule for integration by parts. So this u and this v dash, this is what we need to assign to some function that involves the product of two functions when we're integrating. So this choice of which function is u and which function is v dash is quite important. So let's start off with our first example, and we'll explore how the choice of u and v dash impacts our ability to solve the integral. Example 1, let's find the integral of x times e to the x. Now, before we get into using integration by parts, just notice how there's no substitution here that would make this any easier, right? So this is our first integral where previously we wouldn't have been able to do it. Alright, so here's our integration by parts formula. The integral of uv dash equals uv minus the integral of vu dash, and so now we need to make our choice. Like I said, we're going to do this both ways just to compare. So option 1, we will set u equal to x and v dash equal to e to the x, and option 2, we'll swap that around. So u is equal to e to the x and v dash is equal to x. Alright, let's do these two options side by side, one step at a time. And so the first thing to do is just to find our u dash and our v. So we need to differentiate our u, so u dash equals 1 in this case, and over here u dash equals e to the x. And then we need to integrate to get our v. So we get v equals e to the x over here, and over here the integral of x is half x squared. Alrighty, now we can take these four values and plug them in to our formula. So for option 1, we have that our integral is equal to uv, so that's x times e to the x, minus the integral of VU dash. Oh, sorry, I'll go back up here. This should be VU dash. Alright, so V e to the x times u dash, 1. So just the integral of e to the x with respect to x, of course. Okay, in option 2, the integral would be written as uv, so e to the x times half x squared. Okay, so half x squared and e to the x are multiplied together, minus the integral of vu dash, so or half x squared times e to the x. And that's with respect to x. Alright, let's have a little pause and compare these two. Which one looks better? Option 1 or option 2? Hopefully we can see that over on option 1, we can now very easily work out the integral of e to the x. It's simply e to the x, and when we tag on our constant of integration at the end, we're done. We have our answer. But when we look over at option 2, what we've got here, we would need to use integration by parts again, because we have a product x squared and ex. We have a product of two functions of x, and in fact this is worse than before. If you compare our original question and you compare what we have here, this is even messier. So clearly option 1 is the way to go. The choice is important. But how do we always know what is the best choice? Before we get on to talking about a handy little guide to choosing our u and our v dash, I would just encourage you to look at this answer that we got here over on the left and just go and differentiate that and check that you do in fact go back to this function, x times e to the x. So just a little challenge for you now if you want to pause the video and go and differentiate our answer. The Laurie rule is used to determine which function should be u, which is the function that ends up being differentiated. So Laurie is an acronym, and so starting with the L is for logarithmic functions. So we would choose logarithms to be u first if they popped up. The next is inverse trig functions. Okay, and notice, so far we can't integrate these guys, so that's why they're at the top of the list to differentiate them. Then the next is algebraic functions, then trig functions, and finally exponential functions. So if we think about the reverse order of this, when we start down at exponential and trig, they're really easy to integrate. We know how to do those easily. So that's why we want these guys to be the v dash, because we can integrate them. Algebraic functions, we can integrate them, but like that first example we did, we know that their powers increase when we integrate. So if you've got a quadratic and you integrate it, it'll go up to a cubic. So if you can set these guys to be the u function over trig or exponential, you can reduce their power as you differentiate them. Alrighty, let's do our second example, and we'll use the Laurie rule to help us choose. So we have the integral of x multiplied by sine x. So according to Laurie, algebraic comes before trigonometric. So we're going to set our u to be x, and therefore our v dash will be sine of x. And so we know that uv dash, the integral of that, can be written as uv minus the integral of v u dash. So let's go ahead and do that here, although it might be a good idea, like I said, just to list out what is u dash. So the derivative of x is 1. And what's v? So what's the integral of sine x? Well, the integral of sine x is negative cos x. Okay, remember, if we differentiated cos, we get negative sine, and so therefore we need negative cos. Alright, so we have our 4 different values. Let's go ahead and plug them in. So uv is x times negative cos x. So I'll just put the minus out the front. And then we need to take away the integral of vu dash. So that is negative cos x times 1, or just negative cos x. So if we take the negative out the front of our integral, then that combines with this negative to form a positive. Alright, second line of working. And we can see that the integral we now have is quite straightforward. The integral of cos is simply sine. Adding in our constant of integration, and there we go. There's our answer. Once again, feel free to differentiate this answer that we just got and see if you go back to x sine x. Okay, example 3, we have the integral of ln x. So we know that we can't do this with our old methods, substitution and the like, but also upon first inspection it seems like we can't do it via integration by parts either. Why is that? Well, there's only one function, ln of x. So what do we do? Well, the trick is to set this function to be u, right? It's a logarithm, so it's the top of Laurie. And then we just multiply them by 1. And that's what we set as our v dash. So ln x is our u, and 1 is our v dash. And now we can go ahead and apply our uv minus vu dash. So just doing our little list off to the side, the derivative of ln x, that's 1 on x, and the integral of v dash, v, is x. Okay, so we have uv, so ln x multiplied by x, which we'll put the x first, just makes it a bit clearer, minus the integral of vu dash, so x times 1 on x. Now in this particular case, x times 1 on x, that's actually quite nice because they cancel. And so we just have the integral of 1. The integral of 1 is, of course, x. And so there we go. If we wanted, we could drag out x as a common factor, but we'll just leave it like this. So we've just found the integral of ln x. And yeah, once again, double check it if you like, using the product rule for differentiation. But let's go on to an example now that involves definite integrals. Because so far, we've just been dealing with indefinite integrals, haven't we? So the thing to keep in mind is that whenever we have a definite integral, such as this one, in the end, when we get our integral function, we then apply the fundamental theorem of calculus, where we plug in 2 and 1 in this case and evaluate. And so we need to do the same kind of thing. Alright, first let's choose our u and v dash. So we have an algebraic function and we have a logarithm. So that means, according to Laurie, we want to choose ln x as u, and so x is v dash. That means that u dash is 1 on x, and v, when we integrate x, is half x squared. So first up is uv, so that's ln x times half x squared. So let's put the half x squared first, that'll look a bit nicer. And so this needs to be evaluated according to the fundamental theorem of calculus. So I might actually just put this in now so that we don't forget, but it can be done at the end as well. And then we need to take away the integral, and it's still within the same limits, the integral of vu dash. So I might just give ourselves a bit more room. And the integral of vu dash, what's that? Well, that is our half x squared and our 1 on x. And so like the previous example, we get a little bit of cancelling that we can do in this integral before we evaluate it. Now here, I might just drag out the constant 1/2 and not worry about actually evaluating it yet. And likewise here with this integral, let's drag out 1/2. We have the integral between 1 and 2, and x squared times 1 on x. Well, that simplifies just to be x. Alright, so half is a common factor across the whole expression, so let's drag that out. We have our x squared ln x, and then when we integrate x, we get half x squared. So let's write that in here as well. And so this whole thing, we now have to apply the fundamental theorem of calculus. So first up, when we substitute in 2, what do we get? Well, 2 squared is 4, so we get 4 times ln 2. Minus, and then we have half times 2 squared, so half of 4, so 2. Alrighty, and now we need to substitute in 1. So 1 squared is 1, and ln 1, well, that's just 0. Minus, and when we sub in 1 here, we get half times 1 squared, so just a half. We'll leave the half out the front for now. Let's focus on inside the brackets. So we have 4 ln 2 and minus 2 plus a half, that gives us minus 1.5 or minus 3 on 2. And yeah, we could leave it like this. We could expand it back out, might look a bit nicer. So half times 4 is 2, so we have 2 ln 2 minus 3/4. Yeah, looks like a pretty good place to stop. So there's an example of a definite integral. Remember back here we could have plugged in the 2 and 1 into this x squared ln x, but it's probably going to be better just to leave it and then do it all at once at the end. Okay, let's finish up there for this first part, and in the second video we will have a little look at more generalized problems